At this very moment, deep beneath the cold waters of the Norwegian Sea, lies a German submarine carrying enough mercury to poison an entire ocean. 65 tons of liquid death, sealed in steel containers, corroding slowly in the darkness 200 feet below the surface. This is not ancient history. This is happening right now, and there is nothing anyone can do to stop it. The date is February 9th, 1945. The place is a classified submarine pen in Bergen, Norway, one of the last functioning U-boat bases still under German control. Commander Ralph Reimar Wolfram stands on the deck of U-864, a Type 9D2 ocean-going submarine, watching as the final crates are loaded into his vessel. He is 32 years old, a veteran submariner with 2 years of combat experience, and he has never been assigned a mission quite like this one. The crates being loaded into his submarine do not contain torpedoes or ammunition. They contain 65 tons of mercury, packed in steel flasks, each one heavy enough to require 2 men to lift. Alongside the mercury, workers are loading optical glass, technical drawings for jet aircraft, blueprints for rocket engines, and 2 German engineers who will accompany the cargo all the way to Japan. This is Operation Caesar, and it represents one of the most desperate gambles of the dying Third Reich. Commander Wolfram knows the odds. Every submariner in the Kriegsmarine knows the odds by February 1945. The Battle of the Atlantic has been lost. Allied aircraft patrol every sea lane. Radar technology has advanced to the point where submarines can be detected on the surface from miles away. Escort vessels equipped with sonar hunt U-boats with mechanical precision. The Schnorkel breathing device that allows submarines to run their diesel engines while submerged has helped, but it is not enough. German U-boats are being sunk faster than the shipyards can replace them. Of the 1,054 U-boats commissioned during the war, nearly 800 have already been destroyed. 30,000 men have gone to sea in U-boats. 28,000 of them are dead. The survival rate is 7%. Commander Wolfram understands these numbers intimately. He has seen friends die. He has watched submarines leave port and never return. He has attended memorial services where no bodies were present because the bodies were scattered across the ocean floor, trapped in steel coffins that would never be recovered. And now he is being asked to sail halfway around the world, through waters controlled by the enemy, carrying cargo so valuable that its loss could affect the outcome of the war. The Mercury is destined for Japan. By February 1945, Japan is fighting alone. Germany is collapsing. Soviet armies are advancing from the east. British and American forces are pushing from the west. Berlin will fall within 3 months. Everyone knows this, even if they cannot say it aloud. But Japan continues to fight. The Japanese military is preparing for the final defense of the home islands, a campaign they call Operation Ketsugo, the decisive battle that will determine whether Japan survives as a nation or is invaded and destroyed. To fight this battle, Japan needs raw materials. The islands have almost no natural resources. Oil reserves are nearly exhausted. Aluminum production has collapsed. Steel mills are running on salvaged scrap metal. And mercury, essential for manufacturing detonators for bombs and shells, is completely depleted. Without mercury, Japanese factories cannot produce the millions of artillery shells and aerial bombs needed for the final defense. Without mercury, the entire war effort grinds to a halt. Germany still has mercury. The mines in Spain and Italy are still producing. The question is how to get it to Japan. By February 1945, Japan is completely isolated. The American Navy controls the Pacific. American submarines have devastated Japanese merchant shipping. Of the 2,700 cargo ships Japan possessed at the start of the war, fewer than 300 remain operational. The sea lanes between Japan and the Asian mainland are under constant attack. Flying supplies to Japan is impossible over such distances. The only route left is the one route the Allies cannot completely blockade, the submarine run from Europe to Asia. The plan is ambitious to the point of insanity. U-864 will sail from Bergen, travel north around the coast of Norway into the Arctic Ocean, then turn east and follow the northern coast of Russia all the way to the Bering Strait. From there, the submarine will enter the Pacific Ocean and sail south along the coast of Japan to Kure Naval Base. The distance is approximately 13,000 nautical miles. At an average speed of 10 knots submerged and 16 knots on the surface, the journey will take approximately 3 months. 3 months at sea, most of it in enemy-controlled waters, with no possibility of resupply, no friendly ports, no support vessels. 3 months breathing recycled air, eating preserved food, sleeping in shifts, never seeing daylight, never knowing if the next minute will bring detection and death. Commander Wolfram has made long patrols before. His previous mission lasted 78 days. He knows what happens to men during extended deployments. The psychological strain of submarine warfare is unlike anything else in military service. Soldiers in trenches can see their enemies. Pilots in aircraft have the sky around them. Sailors on surface ships can feel the wind and see the horizon. But submariners exist in a sealed metal tube, surrounded by water pressure that will crush them instantly if the hull fails. They hear every sound amplified through the metal walls, the ping of enemy sonar searching for them, the splash of depth charges hitting the water above them, the terrible creaking of the hull under pressure. They know that if something goes wrong, there is no escape. If the submarine sinks in water deeper than 200 feet, the crew will die. There are no parachutes, no lifeboats, no second chances. You go down with your vessel, and the ocean becomes your grave. The crew of U-864 numbers 53 men. In addition to Commander Wolfram, there are 4 other officers: the executive officer, the chief engineer, the navigator, and the torpedo officer. Below them are the petty officers who operate the submarine's systems, the diesel mechanics who maintain the engines, the electricians who manage the battery banks, the radio operators who maintain contact with headquarters, the sonar technicians who listen for enemy vessels, and below them are the ordinary seamen who perform the manual labor that keeps the submarine functional, loading torpedoes, preparing meals, cleaning compartments, standing watch. Most of them are young. The average age is 23. Some are teenagers, 17 or 18 years old, boys who volunteered for submarine service because it seemed adventurous, or because the pay was better, or because they wanted to escape farm labor. Now they are preparing for a mission that will almost certainly kill them. Joining the regular crew are 2 civilian engineers, specialists in jet engine technology, who are being sent to Japan to assist with aircraft development. Their presence adds another layer of complication. Civilians on a combat submarine create problems. They do not understand military discipline. They do not know how to operate in confined spaces. They panic during depth charge attacks. But orders are orders, and Commander Wolfram has no choice but to accommodate them. The engineers are assigned bunks in the forward torpedo room, where they will sleep surrounded by weapons and machinery, listening to the ocean pressing against the hull just inches from their heads. The Mercury itself presents unique dangers. Mercury is toxic. The vapor can cause neurological damage. Prolonged exposure leads to tremors, mood swings, cognitive decline, and death. The steel flasks containing the mercury are theoretically sealed, but submarines operate in hostile environments. Depth charges create shock waves that can crack welds. Pressure changes can compromise seals. If mercury vapor begins to leak into the submarine's confined atmosphere, the crew will become poisoned slowly, suffering symptoms they may not recognize until it is too late. Commander Wolfram has been briefed on the risks. He has been told that the flasks are safe. He does not entirely believe this, but he has no alternative. The mission has been ordered at the highest levels of command. Refusing would be mutiny, and so he watches the Mercury being loaded into his submarine, flask by flask, ton by ton, until the cargo hold is full and the vessel sits lower in the water from the weight. On February 5, 1945, U-864 departs from Bergen. The weather is terrible, which is good for submarines. Heavy clouds and rough seas make it difficult for aircraft to spot vessels on the surface. Commander Wolfram orders the submarine to proceed north at 16 knots, running on the surface to make maximum speed while conditions favor them. The plan is to reach the Arctic Ocean before British aircraft can locate them, then turn east and begin the long journey along the Russian coast. But almost immediately, problems develop. The submarine's diesel engines begin to malfunction. One of the two engines develops a cooling problem that causes it to overheat. The chief engineer reports that a gasket has failed, allowing coolant to leak. The repair will take several hours and must be done in port, where proper tools and replacement parts are available. Commander Wolfram has no choice. He turns the submarine around and returns to Bergen. The mission is delayed before it has properly begun. The submarine spends 3 days in port, while mechanics repair the engine. Commander Wolfram paces the deck, watching the calendar. Every day of delay increases the risk. British intelligence networks are active throughout Norway. Resistance fighters report ship movements to London. The longer U-864 remains in port, the more likely it is that enemy forces will learn of its departure and prepare an ambush. Finally, on February 9th, the repairs are completed. The chief engineer reports that both diesel engines are operational. Commander Wolfram orders the crew to prepare for departure. At 1700 hours, U-864 casts off and heads to sea once again. This time, the submarine travels less than 50 miles before the same engine fails again. The cooling system is not properly repaired. The gasket is leaking worse than before. Black smoke pours from the exhaust. The engine temperature gauge climbs into the danger zone. If the engine catches fire, the submarine will have to surface completely, becoming visible to any Allied patrol aircraft in the area. Commander Wolfram has no choice. He turns the submarine around for the second time and limps back to Bergen, running on one engine, making barely 10 knots, vulnerable and exposed on the surface. The crew is furious. Submariners are superstitious, and 2 failed departures feel like an omen. Men begin to whisper that the mission is cursed. The Mercury cargo makes everyone nervous. Rumors spread that the flasks are leaking, that men are already showing symptoms of poisoning. The chief medical officer examines the crew and finds nothing wrong, but the rumors persist. Morale begins to deteriorate. Sailors who were confident 3 weeks ago now look haunted. Some write letters home, even though they know the letters will not be delivered until after the mission is complete, if it is completed at all. The submarine remains in port for 2 more weeks. This time, the chief engineer insists on a complete overhaul of both diesel engines. Every gasket is replaced. Every seal is inspected. Every bolt is tightened. The engines are tested repeatedly, run at full power for hours at a time, pushed to their limits to ensure they will not fail again. Finally, on February 9th, the chief engineer certifies that U-864 is ready for sea. Commander Wolfram gives the order to depart for the 3rd time. The submarine leaves Bergen in darkness, running submerged to avoid detection. This time, both engines operate smoothly. U-864 travels north along the Norwegian coast, following the deep channels that provide concealment from sonar. Commander Wolfram orders the submarine to remain submerged during daylight hours and surface only at night to recharge the batteries. Progress is slow but steady. By March 1st, the submarine is north of Trondheim, 200 miles from Bergen, and still undetected. But British naval intelligence is not blind. Enigma decryption has given the Allies the ability to read many German military communications. While the specific details of Operation Caesar remain unknown, British analysts are aware that high-value cargo is being moved by submarine from Norway to Japan. The Royal Navy has positioned submarines along the Norwegian coast specifically to intercept German vessels attempting to break out into the Atlantic. One of these submarines is HMS Venturer, a British V-class submarine under the command of Lieutenant James Launders. Lieutenant Launders is 25 years old and one of the most skilled submarine commanders in the Royal Navy. He has already sunk one German U-boat, U-771, during a patrol in November 1944. That attack was remarkable because it was the first time in history that one submarine sank another while both vessels were completely submerged. Submarine versus submarine combat is extraordinarily difficult. Surface ships can see each other and maneuver accordingly. Submarines operate blind, relying entirely on sonar, and sonar is imperfect. It can detect the sound of another vessel, but it cannot provide precise targeting information. Shooting torpedoes at a submerged target is like shooting at a ghost. You know approximately where it is, but you do not know its exact position, its speed, its direction, or its depth. You must calculate all of these variables, aim your torpedoes at where you think the target will be when the weapons arrive, and hope you are correct. Lieutenant Launders had done this successfully once. He is about to do it again. On February 9th, the same day U-864 departs Bergen for the second time, British naval intelligence intercepts a German radio transmission indicating that a high-value submarine will be transiting the Norwegian coast. The message does not provide specific details, but it is enough. HMS Venturer is ordered to patrol the waters off Fedje Island, a small rocky outcrop about 50 miles north of Bergen. The area is a natural choke point. Submarines leaving Bergen must pass through this region to reach the open ocean. Lieutenant Launders takes his submarine to the area and waits. For days, nothing happens. HMS Venturer patrols slowly back and forth, listening. The sonar operator sits in darkness, wearing headphones, listening to the sounds of the ocean, the clicks and whistles of whales, the hum of distant merchant ships, the rhythmic pinging of their own sonar pulses bouncing off the rocky bottom. Submarine warfare is mostly waiting. Hours of boredom interrupted by minutes of terror. The crew maintains watch in shifts, trying to stay alert, knowing that if they miss the telltale sound of a German submarine, their target will escape, and all of this will have been for nothing. Then, on February 9th, at approximately 1900 hours, the sonar operator hears something. A faint mechanical sound, rhythmic and regular, moving through the water. It is too slow to be a surface ship, too deliberate to be a whale. It is another submarine. Lieutenant Launders is summoned to the sonar station. He listens through the headphones himself, confirming the contact. Yes, this is a submarine, and it is German. British submarines make a different sound. American submarines make a different sound. Soviet submarines make a different sound. Lieutenant Launders has been trained to recognize them all, and this is definitely German. He orders HMS Venturer to pursue. Tracking a submerged submarine is an art form. The target is invisible. You cannot see it, cannot observe its wake, cannot watch its movements. You can only listen, and what you hear is distorted by water temperature, salinity, depth, and distance. Sound travels differently through water than through air. It bends around objects, reflects off the seafloor, creates echoes and false contacts. The sonar operator must filter out all of this noise and focus on the one sound that matters, the propeller noise of the enemy submarine. HMS Venturer follows U-864 through the night. Lieutenant Launders maintains a distance of approximately 2 miles, close enough to track the target, but far enough to avoid detection. German submarines are equipped with hydrophones that can detect the sound of pursuing vessels. If U-864 realizes it is being followed, Commander Wolfram will take evasive action, diving deep, changing course, shutting down engines to become silent. The hunt will become exponentially more difficult. So Lieutenant Launders tracks his target carefully, like a predator following prey, waiting for the perfect moment to strike. At midnight, U-864 surfaces. Commander Wolfram needs to recharge his batteries. The submarine has been running submerged for 6 hours, and the battery banks are depleted. Without power, the submarine cannot operate its electrical systems, cannot run its motors, cannot maintain depth control. The diesel engines must be started, and diesel engines need air. So, U-864 rises to the surface, opens its hatches, and begins sucking in fresh air while the engines rumble to life. HMS Venturer hears the German submarine surface. The sound signature changes immediately. Instead of the quiet electric motors, the sonar operator now hears the loud clattering of diesel engines. Lieutenant Launders brings his own submarine to periscope depth and extends the periscope, searching the darkness. But visibility is poor. The night is overcast, the sea is rough, and the German submarine is running without lights. Lieutenant Launders can hear U-864, but he cannot see it. He considers surfacing and attacking with deck guns, but that would expose HMS Venturer to counterattack. German submarines carry anti-aircraft guns and machine guns specifically to defend against surface attacks. If Commander Wolfram sees HMS Venturer approaching, he will open fire, and the battle will become a gunfight, which is unpredictable and dangerous. Lieutenant Launders decides to wait. He will attack when U-864 submerges again. At 0200 hours, U-864 dives. The batteries are recharged, the diesel engines are shut down, and the submarine slips beneath the surface once more. Commander Wolfram sets a course northeast, following the Norwegian coast, maintaining a depth of 100 feet. He does not know he is being followed. HMS Venturer's sonar has been passive, listening without transmitting, giving away no indication of its presence. Commander Wolfram believes he is alone in the dark water. Lieutenant Launders begins his attack. He must solve a complex geometric problem. U-864 is traveling northeast at approximately 8 knots at a depth of 100 feet. HMS Venturer is 2 miles behind, traveling at 9 knots at a depth of 50 feet. The torpedoes Lieutenant Launders will fire travel at 40 knots and run in a straight line. He must calculate where U-864 will be when the torpedoes arrive and aim at that future position. But he does not know U-864's exact speed, exact depth, or exact course. He can only estimate based on the sound of its propellers and the direction the sound is coming from. It is like throwing a dart at a moving target while blindfolded. Lieutenant Launders makes his calculations. He factors in water temperature, which affects torpedo speed. He factors in the distance to target, which determines travel time. He factors in the possibility that U-864 might change course or depth during the attack. He decides to fire a spread of 4 torpedoes, each one aimed at a slightly different position, creating a pattern that will cover the most likely area where the target will be. If U-864 continues on its current course, at least 1 torpedo should hit. If U-864 changes course, there is still a chance that one of the other torpedoes will intercept it. At 0312 hours, Lieutenant Launders gives the order. The torpedo tubes are flooded. The outer doors are opened. 4 torpedoes are loaded and ready. The firing solution is set. Lieutenant Launders takes a breath and says the word every submarine commander dreads having to say. Fire. 4 torpedoes launch from HMS Venturer in rapid succession. Each one leaves the tube with a compressed air charge that sends it into the water at 40 miles per hour. The weapons are Mark 8 torpedoes, each one 21 feet long, weighing 3,500 pounds, carrying 600 pounds of explosive in the warhead. They are not guided. Once they leave the submarine, they travel in a straight line until they either hit something or run out of fuel and sink. Lieutenant Launders has done everything he can. Now it is a matter of mathematics and luck. Inside U-864, Commander Wolfram is unaware of the attack. The submarine is running quietly, maintaining course, the crew settling into the routine of patrol. Men are sleeping in their bunks, exhausted from weeks of stress and false starts. The engineer on watch monitors the gauges, checking temperatures and pressures, making small adjustments to keep the systems optimal. The sonar operator listens to the ocean, hearing nothing unusual. And then, suddenly, he hears it, the high-pitched whine of torpedo propellers. "Torpedoes in the water," he shouts. The alarm sounds throughout the submarine, a harsh metallic clang that wakes every man instantly. Commander Wolfram is in the control room within seconds. "Where?" he demands. The sonar operator points to his instruments. "Bearing 270, closing fast, multiple contacts." Commander Wolfram makes a decision in less than 3 seconds. He cannot outrun torpedoes. They are faster than his submarine. He cannot surface. That would make him an easier target. His only option is to dive, go as deep as possible, and hope the torpedoes pass overhead. "Emergency dive," he orders. "All ahead full. Take us to 200 feet. The submarine's nose pitches downward. Water floods into the ballast tanks. The electric motors scream as they push the submarine toward the ocean floor. Men grab onto railings and equipment to keep from sliding forward. The depth gauge spins 110, 120, 130 feet. Commander Wolfram watches the gauge and listens to the sonar operator calling out the torpedo positions. Still closing, bearing unchanged, 1,000 yards. At 150 feet, the first torpedo passes 10 feet above U-864's hull. The crew hears it, a screaming sound like a circular saw cutting through metal. For 2 seconds, every man holds his breath, waiting for the explosion. But the torpedo is set to run at 100 feet, and U-864 is now deeper than that. The weapon flies past and continues into the distance, eventually running out of fuel and sinking into the depths. The second torpedo arrives 5 seconds later. This one is set to run at 120 feet. U-864 is at 160 feet, still descending. The torpedo passes 20 feet overhead. Again, no explosion. The third torpedo arrives. This one is set to run at 140 feet. U-864 is at 170 feet. The torpedo passes 15 feet above the submarine's conning tower, so close that the crew can feel the pressure wave as it goes by. Still no explosion. Commander Wolfram allows himself a moment of hope. 3 torpedoes have missed. 1 more to avoid, and they will survive. "Level off at 200 feet, he orders. "Maintain this depth." The 4th torpedo is set to run at 160 feet. When Lieutenant Launders calculated his firing solution, he spread his torpedoes across a range of depths, guessing that the target would either maintain its depth or dive to evade. The 4th torpedo is his deepest shot, his gamble that U-864 would try to go deep. At 185 feet, U-864 begins to level off. The diving planes angle horizontal. The ballast tanks stop flooding. The submarine's descent slows, and at that exact moment, the 4th torpedo, running at 160 feet, closes the final distance and strikes U-864 amidships, directly below the conning tower. 600 pounds of explosive detonates against the submarine's pressure hull. The hull is designed to withstand ocean pressure at moderate depths, but it is not designed to withstand a shaped charge warhead detonating at point-blank range. The explosion tears a hole 15 feet wide in the side of the submarine. Water pressure at 185 feet is more than 80 pounds per square inch. The ocean rushes into U-864 with the force of a fire hose. The submarine breaks in half. The forward section, containing the torpedo room and crew quarters, floods instantly. 20 men are in that compartment. They have no time to react. The water hits them like a hammer. They are crushed against equipment, slammed into bulkheads, drowned in seconds. The mercury flasks stored in the forward cargo hold are ripped open by the explosion. 65 tons of liquid mercury spills into the flooding compartment, mixing with seawater, settling in dense silver puddles among the wreckage. The aft section of the submarine, containing the engine room and control room, survives for approximately 8 seconds longer. The watertight door between the compartments seals automatically, cutting off the forward section. But the damage is too severe. The submarine is flooding from multiple ruptures. The batteries are shorting out, producing clouds of chlorine gas. The air is filling with smoke and poison. Commander Wolfram tries to order an emergency surface, but there is no power. The electric motors are dead. The compressed air system is damaged. The submarine cannot blow its ballast tanks. It cannot rise. It can only sink. The aft section hits the ocean floor at 210 feet. The impact crushes the hull further. Water pours in through every crack and seam. The remaining crew, 33 men, die within minutes. Some drown. Some are poisoned by chlorine gas. Some are crushed when equipment breaks loose and tumbles through the flooding compartments. None escape. There are no survivors. On the surface, HMS Venturer waits. Lieutenant Launders listens on sonar for any indication of what has happened. He hears the explosion. He hears the sound of metal tearing. He hears the unmistakable sound of a submarine breaking apart and sinking. And then he hears nothing. Silence. The target is gone. U-864 has been destroyed. Lieutenant Launders surfaces HMS Venturer and scans the area with his periscope. There is debris on the water, pieces of wood, fragments of metal, an oil slick spreading across the surface. But there are no lifeboats, no survivors, no men in the water calling for rescue. Everyone aboard U-864 is dead. Lieutenant Launders records the position, 53 degrees north latitude, 5 degrees east longitude, approximately 2 miles west of Fiji Island. He reports the kill to British Naval Headquarters. HMS Venturer turns south and returns to base. For Lieutenant Launders and his crew, the mission is a success. They have sunk an enemy submarine. They do not know about the Mercury. They do not know that they have just created one of the most dangerous environmental hazards in modern history. For 28 years, U-864 lies undisturbed on the ocean floor. The submarine is 210 feet down, too deep for casual divers, too far offshore to attract attention. The wreckage is scattered across 100 yards of rocky bottom. The forward section, where the Mercury was stored, is torn open and partially buried in sediment. The aft section is more intact, but still heavily damaged. Fish swim through the compartments. Crabs scuttle across the deck. Algae grows on the metal. The ocean slowly reclaims the submarine, rust and corrosion eating away at the steel, weakening the structure year by year. The mercury remains. Liquid mercury is extraordinarily dense. It is 14 times heavier than water. When the flasks broke open during the explosion, the mercury poured out and sank immediately to the lowest points in the wreckage. It pooled in the bilges, in the gaps between hull plates, in the crevices of the machinery. Some of it mixed with sediment and became trapped in the mud. Some of it remained as pure liquid metal, sitting in silver puddles among the wreckage, slowly corroding the steel around it. Mercury is toxic in all forms, but liquid mercury is relatively stable. It evaporates slowly. It does not dissolve in water easily. As long as the mercury remains trapped inside the submarine, contained by the hull and covered by sediment, it poses minimal environmental risk. But submarine hulls do not last forever. In 1973, Norwegian fishermen begin reporting unusual catches in the waters off Fedje Island. Fish with strange lesions, crabs with deformed shells, nets coming up tangled in debris that looks like pieces of rusted metal. The Norwegian Directorate of Fisheries investigates and discovers the wreckage of a submarine on the seafloor. Initially, they assume it is a German U-boat sunk during the war, which is not unusual. Hundreds of ships and submarines were sunk in Norwegian waters during World War II. Most of them are considered war graves and left undisturbed. But when divers examine this particular wreck more closely, they find something unexpected: metal flasks, broken open, with traces of silver liquid inside. They collect samples and send them to a laboratory. The analysis confirms the presence of mercury. And not just traces. The wreckage is contaminated with massive amounts of mercury, far more than any normal submarine would carry. The Norwegian government consults historical records and identifies the wreck as U-864. British Naval Archives confirm the sinking. German military records, captured after the war, provide details about Operation Caesar and the cargo U-864 was carrying: 65 tons of mercury, packed in steel flasks, destined for Japan. The realization is immediate and alarming. If all 65 tons of mercury are still in the wreck, and if the containers are deteriorating, the mercury will eventually leak into the ocean. Mercury poisoning in fish is a well-documented environmental hazard. Even small amounts of mercury in the water can accumulate in the food chain, concentrating in the tissues of fish, which are then eaten by larger fish, which are then eaten by humans. 65 tons of mercury is not a small amount. It is enough to contaminate the entire Norwegian Sea. The Norwegian government commissions a detailed survey of the wreck. In 1975, a team of divers and remote-operated vehicles examine U-864 section by section. They map the debris field, photograph the damage, and attempt to locate all of the mercury containers. What they find is worse than expected. The forward section of the submarine, where most of the mercury was stored, is completely torn apart. The explosion that sank the submarine ripped through the cargo hold, scattering the flasks across the seafloor. Many of the flasks are broken open. Others are intact, but corroding. The divers estimate that approximately 8 tons of mercury have already leaked out of the containers and mixed with the sediment. The remaining 57 tons are still contained in flasks that are deteriorating rapidly. The steel, exposed to salt water for 30 years, is rusting through. Within a few decades, all of the remaining containers will fail, releasing their contents into the ocean. The question becomes what to do about it. The Norwegian government considers several options. The first option is to do nothing, leave the wreck undisturbed, and hope that the mercury remains trapped in the sediment. This option has the advantage of being cheap and requiring no immediate action, but it also guarantees that eventually all 65 tons of mercury will leak into the ocean. The second option is to recover the wreck, raise U-864 from the seafloor, and transport it to land where the mercury can be safely removed and disposed of. This option has the advantage of completely eliminating the threat. But it also has enormous risks. The submarine is fragile. 70 years of corrosion have weakened the hull. Any attempt to lift it could cause the structure to break apart, spilling all of the remaining mercury into the water at once. The third option is to entomb the wreck, cover it with concrete or some other material that will seal the mercury inside and prevent it from escaping. This option has the advantage of being safer than recovery and more effective than doing nothing. But it also has uncertainties. Will the entombment material remain intact for centuries? Will it prevent all mercury leakage? What happens if the entombment fails? For decades, the Norwegian government debates these options. Environmental groups demand action. Fishermen worry about contamination. Scientists conduct studies. Politicians hold hearings. But no decision is made. The wreck of U-864 continues to sit on the ocean floor, slowly releasing mercury into the surrounding water. In 2003, Norwegian authorities finally decide to act. They choose the entombment option. The plan is to cover the wreck with a layer of sand and gravel, then cap it with a layer of concrete and rock. The covering will be 6 feet thick, heavy enough to prevent the mercury from migrating upward into the water column. The project will cost approximately $25 million and take several years to complete. But before the entombment can begin, environmental groups file lawsuits. They argue that covering the wreck will make it impossible to recover the mercury later if better disposal methods are developed. They argue that the entombment might fail, and then Norway will have an even bigger problem. They argue that the only responsible solution is to recover the wreck, remove the mercury, and dispose of it properly. The lawsuits delay the project for years. The Norwegian government commissions more studies. Engineers develop more detailed plans. Environmental assessments are conducted. Public hearings are held. By 2007, the condition of the wreck has deteriorated significantly. New surveys show that more mercury has leaked out. The steel flasks are corroding faster than previous estimates predicted. Some of the containers have rusted through completely. The sediment around the wreck shows mercury concentrations thousands of times higher than safe levels. Fish caught in the area show elevated mercury levels in their tissues. The contamination is spreading. The Norwegian Coastal Administration finally moves forward with the entombment plan. In 2008, work begins. A barge is positioned above the wreck site. Equipment is lowered to the seafloor. The first layer of sand is carefully placed over the submarine. The work is slow and difficult. The seafloor is rocky and uneven. The wreck is fragile and unstable. Any disturbance could cause the remaining mercury containers to rupture. Workers operate remote-controlled equipment from the surface, using cameras and sensors to guide their actions. They work in shifts around the clock, slowly building up layers of material over the wreck. And then, disaster strikes. In 2009, during the entombment work, sensors detect a sudden spike in mercury levels in the water. One of the remaining flasks has ruptured, releasing liquid mercury into the ocean. The work is immediately halted. Divers investigate and discover that the vibrations from the construction equipment have caused part of the wreck to collapse. Several mercury containers have been crushed, spilling their contents. An estimated 2 tons of mercury have been released into the water. The Norwegian government faces a crisis. The entombment project, intended to contain the mercury, has instead released more of it. Environmental groups demand that the project be abandoned. Fishermen demand compensation for contaminated catches. Scientists warn that the situation is becoming critical. The mercury concentrations in the surrounding water are now high enough to pose a significant health risk. Fish populations in the area are showing widespread contamination. The food chain is being poisoned. After extensive analysis, Norwegian authorities make a controversial decision. They will continue with the entombment, but they will modify the approach. Instead of disturbing the wreck further, they will carefully place material around it, creating a barrier that will gradually enclose the submarine without touching it directly. The work will proceed more slowly and carefully. Every action will be monitored with sensors and cameras. At the first sign of additional mercury release, the work will stop. The modified entombment continues through 2010, 2011, and 2012. Thousands of tons of sand, gravel, and rock are placed around and over the wreck. The covering gradually grows thicker. By 2013, the wreck is completely buried under 6 feet of material. Sensors are installed to monitor mercury levels in the surrounding water. The site is marked as permanently restricted. Fishing is prohibited within a 1-mile radius. The entombment appears to be working. Mercury levels in the water begin to decrease. Fish caught outside the restricted zone show lower contamination levels. The immediate crisis seems to have been contained. But Norwegian environmental authorities know that this is not the end of the story. The entombment is not permanent. The materials covering the wreck will settle and compact over time. Storms will erode the covering. Ocean currents will wash away sediment. Eventually, the wreck will be exposed again. And when that happens, the mercury will start leaking once more. The long-term plan is to monitor the site indefinitely. Sensors will detect any increase in mercury levels. If the covering fails, additional material will be added. If necessary, the entire entombment will be rebuilt. This will continue for decades, perhaps centuries, until the mercury is finally neutralized by chemical processes or until technology advances to the point where safe recovery becomes possible. Today, in 2025, the wreck of U-864 remains buried beneath the Norwegian Sea. The 65 tons of mercury it carried are still there, sealed under layers of sand and rock, slowly corroding in the darkness. Norwegian authorities monitor the site continuously. Environmental scientists study the long-term effects of mercury contamination in the surrounding ecosystem. Fishermen avoid the area, and the ocean continues its slow, patient work of reclaiming what humans left behind. The story of U-864 raises fundamental questions about warfare, technology, and environmental responsibility. In February 1945, when Commander Wolfram loaded 65 tons of mercury onto his submarine, no one considered what might happen if the cargo ended up on the ocean floor. The mission was urgent. The material was essential for Japan's war effort. The risks of the journey were calculated in terms of military success or failure, not environmental consequences. No one imagined that 80 years later, the wreck would still be poisoning the ocean, creating a problem that has no perfect solution. The mercury aboard U-864 was not a weapon. It was raw material, intended for manufacturing detonators and explosives in Japanese factories. But in a sense, it has become a more persistent threat than any weapon the submarine could have carried. Torpedoes explode and disappear. Bombs destroy their targets and leave craters that eventually fill with vegetation. But mercury endures. It does not decay. It does not become less toxic over time. It simply spreads, contaminating everything it touches, accumulating in living tissue, poisoning the food chain from the smallest microorganisms to the largest predators. The technical specifications of U-864 tell part of the story. The Type 9D2 was designed as a long-range cargo submarine capable of carrying supplies across vast distances. It was 287 feet long, 30 feet wide, with a displacement of 1,781 tons when surfaced. The submarine could carry up to 252 tons of cargo, in addition to fuel, weapons, and provisions. It had a maximum surface speed of 19 knots and a submerged speed of 7 knots. The range was approximately 12,400 miles at 12 knots on the surface, making it one of the longest-ranged submarines in the German fleet. These capabilities made the Type 9D2 ideal for cargo runs between Europe and Asia. Germany and Japan were allies, but geographically separated by thousands of miles of enemy-controlled territory. Surface shipping between the two nations was impossible by 1945. Allied naval forces controlled the Atlantic and Indian Oceans. Allied air forces dominated the skies. The only way to move cargo between Germany and Japan was by submarine, traveling submerged through waters where surface vessels would be immediately attacked. Operation Caesar was part of a larger program of technology exchange between Germany and Japan. Throughout the war, the two nations shared military technology, industrial techniques, and strategic materials. Germany sent Japan blueprints for jet engines, rocket technology, advanced optics, and radar systems. Japan sent Germany samples of rubber, raw silk, quinine, and other materials unavailable in Europe. The submarines that carried these cargoes operated under code names like Monson and Yanagi, traveling routes that stretched halfway around the world. But by February 1945, these operations had become nearly suicidal. The Allies controlled every ocean. Radar coverage was comprehensive. Sonar technology had advanced to the point where submarines could be detected at great distances. Allied submarines patrolled every likely transit route. The chance of a German submarine successfully traveling from Norway to Japan was minimal. U-864 was one of several submarines that attempted the journey in early 1945. None of them succeeded. All were sunk before reaching their destinations. The crew of U-864 knew the odds. Commander Wolfram had discussed the mission with his officers before departure. They understood that they were unlikely to survive, but they also understood that the cargo was important. Japan's war effort was collapsing. Without raw materials, Japanese factories would stop producing weapons. Without weapons, Japanese forces could not resist the Allied advance. The Mercury aboard U-864 represented months of Japanese ammunition production. It represented the possibility that Japan could continue fighting, at least for a while longer. Whether this was a worthy goal is debatable. By February 1945, Japan had already lost the war. The atomic bombs that would force Japanese surrender were months away from completion. The Soviet Union was preparing to enter the war against Japan. The Americans were advancing across the Pacific, island by island, getting closer to the Japanese home islands. Nothing Germany could send to Japan would change the outcome. But the crew of U-864 did not know this. They believed they were carrying cargo that mattered. They believed their mission was important. And so they loaded the Mercury and sailed into the Norwegian Sea, where they met HMS Venturer and died. The technical details of the sinking demonstrate the sophistication of submarine warfare by 1945. Lieutenant Launders's attack required solving multiple problems simultaneously. He had to track a submerged target using only sound. He had to predict the target's future position based on incomplete information. He had to calculate the trajectories of 4 torpedoes and distribute them across a 3-dimensional space in a pattern that would maximize the probability of hitting the target. And he had to do all of this while keeping his own submarine undetected, maneuvering quietly, avoiding giving away his position. The attack demonstrated the highest level of submarine tactics. It was a masterpiece of naval warfare. It was also the death sentence for 53 men and the beginning of an environmental disaster that continues today. The aftermath of the sinking reveals how little the combatants understood about the long-term consequences of their actions. When Lieutenant Launders reported the sinking of U-864, he described it as a successful attack on an enemy submarine. He did not mention the cargo because he did not know about it. The British Admiralty recorded the sinking as another U-boat destroyed, another small victory in the Battle of the Atlantic. No one investigated what U-864 had been carrying. No one surveyed the wreck site. No one considered the possibility that the cargo might pose a long-term threat. The submarine sank, the war continued, and everyone moved on. This pattern repeated across thousands of shipwrecks from World War II. Warships sank carrying fuel oil, ammunition, chemical weapons, and hazardous materials. Merchant ships went down loaded with industrial chemicals, toxic metals, and dangerous cargo. Most of these wrecks were never surveyed. Their contents were never catalogued. They simply disappeared beneath the waves and were forgotten. Decades later, many of them are leaking their contents into the ocean, creating environmental problems that no one anticipated. The wreck of U-864 is unusual only because we know what it was carrying. We know because German records survived the war, and because those records were specific about Operation Caesar and its cargo, but there are thousands of other wrecks from World War II that remain unidentified and unsurveyed. Some of them are certainly carrying hazardous materials. Some are probably leaking, but we do not know which ones or where they are or what they contain. They are time bombs scattered across the ocean floor, waiting to release their contents. The Mercury from U-864 illustrates a broader problem with ocean dumping of hazardous materials. For decades, nations treated the ocean as an infinite disposal site. Unwanted chemicals were loaded onto ships and dumped at sea. Obsolete weapons were scuttled in deep water. Radioactive waste was sealed in drums and dropped into ocean trenches. The assumption was that the ocean was so large and so deep that anything dumped there would be diluted to harmlessness. This assumption was wrong. Mercury is an excellent example of why ocean dumping fails, even though the Mercury from U-864 is sitting on the bottom of the Norwegian Sea. 200 feet down, buried under 6 feet of sand and rock, it is still entering the food chain. Mercury dissolves very slowly in seawater, but it does dissolve. Tiny amounts are constantly being released from the wreck site. These tiny amounts are absorbed by bacteria and plankton. Small fish eat the plankton and accumulate the mercury in their tissues. Larger fish eat the small fish and accumulate even more mercury. Predatory fish at the top of the food chain accumulate the highest concentrations, and humans eat those fish, absorbing mercury that originated from a submarine that sank 80 years ago. This process, called bioaccumulation, means that even tiny amounts of mercury in the ocean become concentrated to dangerous levels in seafood. The mercury from U-864 is now distributed across thousands of square miles of ocean. It is in the sediment, in the plankton, in the fish, in the birds that eat the fish, in the marine mammals that hunt in the area. It will remain in the ecosystem for centuries, perhaps millennia, slowly cycling through the food web, being absorbed and re-released, never going away. The long-term effects of mercury contamination are well documented. Mercury is a neurotoxin that damages the brain and nervous system. High doses can cause tremors, memory loss, difficulty concentrating, mood changes, and, in extreme cases, death. Low doses, accumulated over years of exposure, can cause subtle cognitive deficits that are difficult to diagnose. Children and developing fetuses are especially vulnerable. Pregnant women who eat mercury-contaminated fish can pass the toxin to their unborn children, causing developmental problems that may not become apparent until years later. Norwegian health authorities have issued advisories about eating fish caught near the U-864 wreck site. They recommend limiting consumption of certain species, especially large predatory fish that accumulate high mercury levels. They warn pregnant women and children to avoid fish from the area entirely. But enforcing these advisories is difficult. The mercury has spread far beyond the immediate wreck site. Fish migrate over large distances. A fish contaminated near Fiji Island might be caught 100 miles away. Consumers buying fish at markets have no way to know where the fish were caught, or whether they are contaminated. The mercury from U-864 has become an invisible threat, present but undetectable without laboratory testing. The economic impact of the contamination is significant but difficult to quantify. Norwegian fisheries near Fiji Island have been disrupted. Some fishing grounds have been closed. Fish catches from permitted areas must be tested for mercury before they can be sold. The testing adds cost and delay. Some catches must be destroyed because mercury levels exceed safe limits. Fishermen lose income. Processing facilities lose revenue. The contamination affects not just the immediate area, but the entire regional fishing industry, because consumers become concerned about seafood safety in general. Tourism has also been affected. Fiji Island and the surrounding coast are popular recreation areas. Diving, fishing, and boating attract visitors who contribute to the local economy. But the publicity about U-864 and its Mercury cargo has created concern. Some tourists avoid the area. Diving operators must inform customers about the wreck and the contamination. The site has become known not for its natural beauty, but for its pollution. This reputational damage is difficult to measure, but real. The Norwegian government has spent over $50 million on surveying, monitoring, and entombing the wreck. This does not include the ongoing costs of continuous monitoring, periodic maintenance of the entombment, and additional remediation if the covering fails. These costs will continue indefinitely. The Norwegian taxpayers are paying to contain a problem created by a German submarine carrying Japanese cargo during a war that ended 80 years ago. The question of who should bear these costs has never been resolved. Germany and Japan were the parties responsible for creating the problem. Should they contribute to solving it? International law provides no clear answer. The wreck lies in Norwegian waters, making it Norway's responsibility regardless of who created the problem. This raises broader questions about responsibility for wartime environmental damage. Wars create massive environmental destruction. Bombs crater landscapes. Artillery shells contaminate soil with heavy metals. Chemical weapons poison groundwater. Nuclear weapons create radioactive fallout that persists for generations. In the immediate aftermath of war, environmental concerns are secondary to reconstruction and recovery. But decades later, when nations have rebuilt and memories have faded, the environmental legacy remains. Who is responsible for cleaning it up? The wreck of U-864 is relatively small in the context of World War II's environmental legacy. Consider the scale of the problem globally. Tens of thousands of ships were sunk during the war. Many carried fuel oil, which is still leaking from wrecks 70 years later. Some carried chemical weapons. Germany produced thousands of tons of chemical agents during the war. After the war ended, Allied forces dumped captured chemical weapons into the ocean. The Baltic Sea, the North Sea, and various deep ocean trenches became dumping grounds for obsolete chemical munitions. These weapons are now corroding in seawater, and their contents are beginning to leak. Some are washing up on beaches. Fishermen occasionally snag them in nets. The chemicals inside remain lethal. Japan also produced chemical weapons during World War II and used them extensively in China. After the war, Japanese forces dumped chemical weapons in rivers, harbors, and coastal waters rather than allowing them to be captured. China has identified hundreds of locations where Japanese chemical weapons were abandoned. Many of these sites remain contaminated. Some weapons have been recovered and destroyed, but many remain unaccounted for, buried in soil or sunk in waterways, slowly leaking their contents. The United States dumped chemical weapons after World War II as well. Operation Chase, Cut Holes, and Sink 'em involved loading obsolete chemical munitions onto old ships, sailing them out to sea, and scuttling them in deep water. This operation continued into the 1970s. Thousands of tons of chemical weapons now sit on the ocean floor off the American coast. The assumption was that the weapons would be safely contained by the deep ocean. But some of the dump sites are in relatively shallow water. Some are near shipping lanes or fishing grounds, and the weapons are corroding, their chemical contents leaking into the ocean. Nuclear weapons testing added another layer of contamination. The United States, Soviet Union, Britain, France, and China conducted hundreds of nuclear tests in the atmosphere and underwater between 1945 and 1980. These tests released enormous quantities of radioactive material into the environment. Much of it settled into the ocean. Some test sites remain contaminated today. The Bikini Atoll, used by the United States for nuclear testing in the 1940s and 50s, is still too radioactive for permanent habitation. The seafloor around the atoll contains radioactive sediment that will remain dangerous for thousands of years. The cumulative effect of all this wartime contamination is staggering. The oceans have absorbed chemical weapons, radioactive materials, toxic metals, fuel oil, ammunition, and countless other hazardous substances from wars fought decades ago. Most of this contamination is invisible. It does not create dramatic headlines or immediate crises. It simply accumulates in the environment, entering the food chain, concentrating in living tissue, causing subtle harm that is difficult to detect and impossible to completely reverse. The wreck of U-864 and its Mercury cargo is a small piece of this larger story, but it is a piece we can see and measure and attempt to remediate. It provides a concrete example of how wartime actions create environmental consequences that persist for generations. It demonstrates that the true cost of war extends far beyond the casualties and destruction visible during the conflict. The environmental legacy of war continues long after peace treaties are signed and soldiers return home. Commander Wolfram and his crew did not set out to create an environmental disaster. They were following orders, carrying out a mission they believed was important. They did not choose to die in the cold waters off Norway. They did not choose to become part of a pollution crisis that would persist for generations. They were simply sailors doing their duty in a war they did not start and could not control. Their deaths were tragic. The environmental consequences of those deaths compound the tragedy. Lieutenant Launders and his crew acted correctly, according to the rules of naval warfare. They identified an enemy submarine, tracked it, and destroyed it. They accomplished their mission and returned safely to base. They had no way of knowing what cargo U-864 was carrying. They had no way of anticipating the long-term consequences of the sinking. They were skilled professionals executing their duties in wartime. They succeeded brilliantly at what they were ordered to do. That their success created an environmental problem was not their fault. It was not anyone's fault in the sense of deliberate wrongdoing. It was simply a consequence of warfare in an era when environmental considerations were not part of military planning. The challenge today is dealing with consequences that no one intended and no one anticipated. The mercury is there. The wreck is leaking. The contamination is spreading. Assigning blame accomplishes nothing. The question is what to do about it. And the answer, unfortunately, is that there is no perfect solution. Recovering the wreck is dangerous and expensive, and might release more mercury than it contains. Entombing the wreck is less dangerous, but not permanent, and requires ongoing maintenance indefinitely. Doing nothing guarantees that the problem will get worse. Every option has drawbacks. Every option costs money. Every option requires commitment across generations. Someone will be monitoring and maintaining the U-864 site 100 years from now, long after everyone involved in the original decision-making is dead. This is the ultimate legacy of U-864. Not the brief combat between two submarines in February 1945. Not the destruction of a German cargo vessel. Not even the deaths of 53 men. The legacy is an environmental problem that will outlast everyone currently alive, that will require resources and attention for longer than most nations have existed, that demonstrates how a single military operation can create consequences that echo across centuries. The Mercury sits on the ocean floor, 200 feet down, buried under sand and rock, slowly corroding in the darkness. It will still be there when everyone reading these words is dead. It will still be leaking into the ocean when their children are dead. It will still be poisoning the food chain when their grandchildren are dead. The half-life of the problem is measured not in years, but in geological time. The mercury does not decay. It does not become less dangerous. It simply persists. A reminder that some actions cannot be undone, some mistakes cannot be corrected, some consequences cannot be escaped. And that, ultimately, is what makes the story of U-864 important. It is not just history. It is not just a tale of submarine warfare or environmental contamination. It is a demonstration of how decisions made in one moment can create obligations that extend across generations. It is a lesson about the long shadow cast by warfare, about the hidden costs of conflict that continue accumulating long after the fighting stops. The submarine lies in darkness, broken and corroded, slowly dissolving into the ocean floor. The men who sailed in it are long dead. The war they fought is history. The nations they served have changed beyond recognition. But the Mercury remains, 65 tons of toxic metal sealed under layers of sediment and rock, waiting with patience that exceeds human comprehension, leaking slowly into the surrounding water, molecule by molecule, year after year, century after century, long after everyone involved has been forgotten, long after the reasons for the original mission have become incomprehensible, long after the war itself has faded into distant history. This is the underwater time bomb. Not a weapon that will explode in some dramatic moment. A poison that will continue spreading for longer than empires last. A problem without a solution. A consequence without an end. A reminder that what we do echoes in ways we cannot predict, creating obligations we cannot fulfill, generating costs we cannot pay. The ocean is patient. The Mercury is patient. And somewhere in the cold darkness beneath the Norwegian Sea, U-864 waits, slowly releasing its cargo into the water, one molecule at a time, forever.